So in an overwhelming vote, 66% of people voted to do the math of neural networks. And by 66%, I mean 2 people voted for that, and one person voted for random forests. So, I mean, democracy wins.
Yeah.
Put another way, they won by 1 vote.
They did win by 1 vote, yes. however you want to put it.
It's very close.
So, we're going to get more into the math of neural networks. In particular, we're going to get into optimization techniques and regularization techniques. For those who are in the like fundamentals of AI class, this will be very, 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 very familiar to you. For those who weren't, you can just feel free to ask questions. Or if you already know everything, I don't know what you're doing in class. So anyway, so we're going to just start with the code. So we're going to start with imports, NumPy for the actual being able to do like play with numbers essentially, matplotlib in order to generate cool plots, sklearn data sets in order to get our data, and math for some math functions. This NumPy random seed is for reproducibility, so it just sets the random seed so they'll all have about the same. They'll all have about the same.
It's kind of locked or something.
They'll all have about the same numbers. Random numbers.
Well, maybe it's okay now.
No, it's
It's still spooling.
all good.
This machine seems to be locked.
Oh, sorry. So we're going to define a function to load our data set. We're just going to get training data, train X and train Y, our features and our labels from sklearn data sets. Make moons, that's because they're going to be like little moons. And noise is what is going to allow the red to cross over to the blue and vice versa. It's it's going to be a more noisy data set.
Sorry, what card do I need to put in there?
Is there? Can you try this one?
Oh, nice. Oh, okay. Oh, I guess there is one left.
Oh, okay, great.
Thanks.
Okay, so the noise is going to be how much traciness our data has.
What's that sound? You've got a microphone someplace. Yeah, it seems to be up there where you are. There you go.
Wow, I don't know why that was happening. Sorry. I hope nobody's ears got too destroyed. Anyway.
Oh, sorry, what's the block booking pass? I guess.
1, 2, 3, 4. Good. Did it work?
Yes,
Great.
okay.
All right. So we're going to load our data set. We're going to make moons. So the little moons. If you want to increase the noise to 0.8, it would be a lot more, and if you reduce it to 0, it'll be a lot less. This is just to scatter. It's going to essentially, we're going to be able to graph it. We're going to return our training data, so all the features, and our testing data. The testing data is going to have a label of a 0 or a 1, and that's going to be the red dot or the blue dot. All right, and then load our data set. And then, as I said before, we can change the noise if we want it to be 0.8. It'll just be a lot messier. But we're going to stick to 0.2 because that's much easier. And we're going to declare our activation functions. The activation functions that we talked about last week are the sigmoid activation function, which looks similar to this at 0 and 1. So at, this should actually be closer to That should be closer to 0.5. But the sigmoid activation, when you have an x that's like at 0.5, it should be at, if you have a y that's at 0.5, it should be at 0, and you just patch your data through it, and it essentially squishes it into a simpler form, in a way. That's actually not super true. It's more like a filter, in a way. It'll filter your data and make it in a way that the model's going to be able to understand a little better. The ReLU activation function is going to look more similar to this, where anything at 0 is going to be at 0, and anything above 0 is going to be at 1, or at x. It's going to be the same thing out as you put it. All right? So,
Quick question about
Yes.
activation functions. They are part of input neurons, right? They're not in the hidden neurons.
yeah, in a way. So, when we have our neural network, I'm just going to, I don't feel like going all this line, so sorry about that. We have a neural network that looks like this. In each of these circles, we can think of it split in half, in a way. So inside will be our input data, it'll pass through, and then inside of it, it'll be activated with one of these activation functions. And actually don't remember the notation. I'm just going to call it XA. So X activated is going to output through it. So inside one of these neurons is, the neuron essentially is the activation function, in a way. It's where all the matrix multiplication happens. So you're also going to multiply by your weight, and it's going to be activated.
Yeah, but it's still in the first row.
Yes, it's in each one of these.
Oh,
It's in every single one.
Oh, each of them.
Yes.
All right.
Yes, each one. Sorry. So we have our activation functions. Beautiful. And we're going to initialize our parameters. This is our y equals mx plus b, our m and our b, our weights and our biases. We're just going to get the number of layer dimensions that we put in. And we're going to just create a dictionary of parameters where the weight will be, let's say, weight 1, weight 2, weight 3, however many parameters we have. And then we're going to return our actual parameters. This is going to be our cost function, our loss function, whatever you want to call it. This is just going to be the measure of how good or bad our model does. In this situation, we're using cost entropy loss. Which for the most part looks like 0 to 10 or I, I don't remember. And the I, let's say negative, what's negative here? Plus. And that's why this is what happens. Okay. So this is what our activation function is essentially going to be, our cost, J, or cost, whatever you want to call it. But essentially what's going to happen is that this will compute the loss of our y hat, which is going to be our it's going to be our output, our label, multiplied by the true label. And that's going to be added with the y. Oh, it's actually just over here. Sorry. Yeah, that should be y hat. So our y hat, our y with a little caret on top, multiplied by log of y, which is going to be the label. So label, pred, label, and it's going over here is going to be the prediction minus 1, and the log of y. And that's going to return something that we are going to be able to use. And then I'm going to multiply by 1 over m, which is the number of examples that we have, as we can see here. Now we're going to move on to our forward propagation function. We're going to pass in our parameters, which are going to be our x, our w, our weights, our biases, our x, which is going to be the input data. We're going to call it out right here. This is actually poorly done. I should have just over it, but it doesn't matter. And this is going to be where all the actual math takes place. We're going to do the dot product of our weight, of our first weight, and our input data, plus our bias, and then we're going to pass that through the ReLU. So this whole thing can be thought of as a single circle. Yes. We're going to do the exact same thing over here, the exact same thing once more. The reason that we want to do the sigmoid at the end is because we're trying to predict a 0 or a 1, and if we recall here, the sigmoid activation function looks somewhat like this, between 1 and 0. And this will squeeze down to 1 or 0, and at this point, it'll be about 0.5. So we can just say, if the prediction says it's above 0.5, there's a better probability that it's above 0.5, we'll say it's a 1, and if it's below 0.5, it's 0. That make sense, everybody? Any questions?
Sure, I mean, I came in late, but just so I'm not that's the whole thing. But so did you start at 6:30?
35.
6:35. Okay.
Ish.
Oh, sure. Okay. So what is the ReLU?
The ReLU function is, sorry. ReLU function looks like this. Where at 0, it's going to return 0, and at anything above 0 is going to return the x, the input, essentially.
So all of those are matrices, W1?
Yeah, so all of these can be thought of as matrices. I mean, you definitely could think of them not as matrices, but we do use matrices just because it's going to be a lot more computationally less expensive. Because if you have 1,000 data points, you can pass every single one of those 1,000 data points through as a matrix, as opposed to doing calculations on the first one, then doing calculations on the second one, and doing calculations on the third one.
Sure. So every one of those W1s, none of those are scalars. Those are actually matrices.
Yes, correct. The B's are scalars.
Okay.
The B's are scalars.
Okay.
But yeah, the W's should have the same shape as the X's. So we can do dot. Then we're going to return everything. I should be running these. Now here's where we're going to our backpropagation. Very similar to last week. We're just going to shape of however many data points we have. We're going to get all of our cache from right here. We're going to do the average of A minus Y, which is going to be the output versus the predicted value. I mean, the output versus the true label. We're going to go back and multiply that difference times the A2, which is going to be from up here. So we're just going back through this entire process, essentially. This is going to be the back propagation step, where we're going to be able to just keep going back and through, and that's how we're going to learn and update our model and our parameters. Any questions about that?
I couldn't repeat it all back, but that's fine.
Was there anything in particular that you're not super?
So, is there a looping mechanism where you reincorporate?
Yes, we're going to do that.
We haven't gotten to that.
But yeah, exactly. So when we actually get to the down here, that's where we're going to go. So I promise that because it's going to have to go through all the data points, then it's going to go back through them and then keep going like that.
You might have mentioned it, but maybe not. I'm curious, this back word.
Back propagation.
Back propagation, right? So it's based on what formula? The one that you wrote before? Or?
Kind of. So we have it's all based on the derivatives of our formulas. So what we'll have is we'll have let's say let's go back to our y equals mx plus b. And so when we keep going through this, and when we're going to forward propagate through this n amount of times, however many layers we have. And then as we go back, we're going to have to find the derivative of that with respect to x. So we're going to, are you familiar with derivatives and calculus at all?
Yeah.
Well, okay, so, so in the simplest terms, it's just a difference from how you got from point A to point B, right? So that's exactly what we're computing. So when we back propagate here, we're going to go back and update our parameters with all of the gradients, all of the results from the derivatives. And then we're going to multiply it by the learning rate, which is going to be a very, very small number. In this case, I think I said like 0.007 or something like that. Just because the actual difference could be very, very big. And when we're trying to map a function, which look like this, let's say this. And we're trying to get to 0 for our loss function, right? But we start here, and if we take the derivative, if we're here, and our predicted value is here, the derivative is going to be very, very, very large. So it's just going to keep bouncing all around. It's probably going to go back out and never reach this point that we want to reach. So by making it a smaller learning rate, we're able to go here and then take a little step, and we're end up here. And we go here, take a little step, and we end up here, and so on and so forth. And that's why we're going to loop through it hundreds and hundreds of times in some cases, and that's how we're going to get to that.
So the learning rate is the step size?
Essentially, yes. It's just going to be how big of a, yeah, exactly, how big
Delta.
of a, yeah, exactly.
So am I understanding correctly? I'm sorry. Like say, first layer we have x and just x. Second layer we have x squared, right? More or less.
Kind of, yes.
And then the third we have x cubed, right?
Mhm.
Right. So that means when we go backwards, then the first derivative is going to be from x cubed, right?
Yeah.
So
yeah,
it's
so
going to be x squared, and then
yeah. So if our output in our, so let's just do it in like the simplest way possible. So let's say we just have like, I don't know. Let's say we have a circle in each one. Just for the sake of simplicity. So if our input's x, and then our output's going to be x squared, x to the third, and then y. Okay? So we're going to calculate the loss with this y and find a derivative there. Then we're going to do the chain rule. So we're going to multiply whatever this is with 3x squared, which is the derivative of this. And that's how we're going to be able to, so we have like the derivative of partial loss over x, respect to x. And then we're just going to keep going, so then we'll have partial L x, well, yes, I guess, sorry, 3x squared plus 2x, and so on. That's going to be how we're going to calculate all of our back propagation. Does that make sense? And then with each of these, at each step, it's going to be how much we're going to change our gradients. So we're going to take this whole thing, in this case, in the weights, and we're going to multiply it by our learning rate, which is going to be like our 0.007 or whatever, or your favorite number. Doesn't really matter too much as long as it's small. And we're going to multiply it by that because this could be a very, very large number. But we don't want that, which is why we have this. We don't want it going here, we want it going here. And that's how we're using the chain rule of calculus is how we're going to just keep going, going, going. And then we're going to eventually get to the local minimum, which is going to be, which our local minimum is going to reduce this to ideally 0. I should have a white hat here. Which is going to essentially reduce this to ideally 0, which means that this is perfect to this. Like it's like a 1-to-1 match in every case. However, we don't exactly always want a 1-to-1 match because that means our model probably isn't generalizing, which we'll see a little bit later. Does that make sense?
Overfitting, right?
Yes, exactly. Any questions about that? We got pretty into the weeds there.
I mean, I have another question. What happens to biases?
Our biases, they're there because they're also going to be updated, as you can see here. Our bias, but just instead of multiplying, it's going to be added together.
Right, so what I mean is, when we start, right, they picked randomly, right?
Yes.
Biases, right? So,
The biases are start at 0.
oh, they started 0.
Biases start at 0, the weights are started randomly.
All right.
So we're going to have no, because we don't want any bias to start, but we just want to give a decent place for the model to start with the weights. Because if we're going to have weights like starting randomly, it's going to start here with, let's say, 0.5, and then over here it'll go to, like this one is at 0.7, so we just want to keep determining how much we want to change each of those.
Right, so, but if we take derivative from constant, you know, bias is constant, right? 0 in this case, right?
Yes.
If we take derivative will be 0. So that means biases that will never change.
We don't need to take the derivative of that, of the bias itself. We want to take the derivative of the entire function. And that's how, and using that is how we're going to change the bias. So we're just going to add or subtract it based on what this is, as opposed to multiplying in the weights case. Good? Is it acceptable?
Sounds good. Thank you.
Any other questions?
The bias, is that mathematically basically just your starting point for the experimentation?
Yeah, so if we go back to our y equals mx plus b example, our bias is going to be this part right here. Or
Okay,
y-intercept,
so
I think it's called.
Formerly called error?
Not exactly the error, not exactly the error.
Okay, all
But
right.
it's just the
It's
it's
the
an
plug.
additional
It's the
starting point in order to tell the model on how we want to graph our equation.
plug. Okay.
And then this is the m is going to be our weights. Okay. In order to make a prediction, we're just going to take the shape again, pass in just zeros. P is going to be our prediction. We want to get our A3 in cache, which is like A3 is our actual prediction. Cache is from up there a little bit more. Is going to be our actual weights and biases, our actual model essentially. And we're just going to pass the A3 in, so like all of the predictions that we have. For anything that's over 0.5 is going to be a 1, anything that's under 0.5 is going to be a 0, and we're going to put the accuracy of how well we did. And then predict dec, I don't remember why I call it dec, but that's just going to make a single prediction as opposed to predict, which will do a whole bunch of predictions. Now that I think about it, this will actually do the exact same thing if you just pass an array of 1, but completely besides the point. Plot decision boundary is just going to be how we're going to make our decision. We're just going to make it beautiful to visually show how well or poorly we did with our model. We don't need to talk about this too much. It's just kind of there. So we're going to get into the actual model. So here we're going to start by declaring gradients and costs. We're going to get our m equals x shape again, just to see how many we have. We're going to declare our dimensions very arbitrarily, I guess. This will just be however many inputs we have. This will be the first line of circles, line of neurons at 20, the second one at 3, and the third at 1 because we want one output. We're going to initialize our parameters with the function that we created before. And this is where all the fun stuff happens. So we're going to, okay, so this, a lot of this other stuff is going to make sense a little bit later. So don't worry quite yet about heap probability, lambda, or anything else, I guess.
Sorry. So x is what?
X's are inputs, are features.
X is an input and y is the prediction.
Yeah, y is the output. So if we go back up here, this is what our input data is going to look like, where x is going to be an array of 2 by n number of dots. I think it's 300.
Okay.
And our y is going to be, each dot is going to be either a 1 or a 0.
So on the, so it looks like you got 2 hidden layers. The first hidden layer
Yes,
is
we have
20 and
20 and then 3.
3. So any reason for picking that? I know, I think you said it's arbitrary. But
It's
is that,
okay. So
is it really arbitrary?
it's not arbitrary at all,
Okay.
because if you have a function that is too simple, if you have something like that, it's going to make it's not going to have the complexity of a graph that you might want. We can actually play with this in a moment when we get to that. But because here we're going to obviously we're going to probably need to draw a line like here. But if we just have if we just have like a one dimensional with one dot, it's just going to probably only going to be able to draw like a linear layer. So by creating more layers / more neurons, it's just going to add another layer of complexity. And that part is the part where it's like, I don't want to say arbitrary, but it's arbitrary in the sense that it's more of you have to develop an intuition on how to do it. It's a lot of just experimenting, failing, experimenting again, failing again, because we can go down, when we go down, we can redeclare the function as opposed to 20, 3, 1. We can do like 2, 2, 1, and then see how we do comparing.
And is your experimentation based on that visualization, or is it, or do you have that?
The experimentation is very, very much based on the data. So if you had very, very complex images, we would have to do a much deeper, like a much longer / wider network. But if we have something like this, what we have is probably fine, and 20 neurons is probably overkill as well. If you're dealing with images that have like 4K pixels, then that is going to require a lot more. And I also recommend, if you have an image of 4K pixels, you probably want to make it so it's not 4K pixels, because that's going to take forever to make it, because it's a lot of pixels. So it's just in the way the intuition of how complex your data is. So in this case, we only have 2 features, but in some cases you have the MNIST data set, which is handwritten character size 784 input X's, input features, is one for each pixel. So, and that doesn't even need that very complicated of a network. So 784 is pretty fine. So yeah, it's all kind of intuition, experimenting, and getting a feel for how complicated of a function that you want to actually graph. Okay, so yeah, we're going to ignore this for now. I promise we'll come back to most of this. That's just because we want to just do forward propagation, and we want to do back propagation. The lambda, well, the lamb and heap prob is going to all make sense in another minute. That's just something for later. So, oh, you know what? Oh, that's fine. Okay. So this is going to be just a regular model with lambda equals 0, key prop equals 1, which, as I said, don't worry about right now. And that's pretty good. And if we go here, we can definitely see that it's overfitting. We can tell that because, so for people who are overfitting is when you're trying to try to see all the data and complex and get like the most complex function you possibly can. So you can see here that like this random blue warp up here, that's bad. This red, whatever peninsula is also very, very bad. But I mean, the general idea is there because ideally we have a function that looks kind of like this. This is bad. And this is also a reason why I did the 20 layers, because I knew it would overfit with so many iterations. So what the idea behind these lectures, this lecture, is the optimization and regularization in order to prevent overfitting. So we're going to start with L2 regularization, which is also known as weight decay. So we're going to multiply, so essentially here, you can see that the idea behind L2 regularization is that we had an extra term when performing our back propagation, which is just going to be our lambda plus our weights over n. We also have to call it lambda because lambda is a reserved keyword in Python. And the reason for this is that we want to penalize very, very large weights. So if we back to the example of this over here, and we have the prediction versus the actual value over here, we don't want to make a huge step like that. Sometimes the learning rate isn't quite enough because it is only just a number. So it is only just like a scaling factor. So L2 regularization is going to help us maybe go from, instead of making a step over here, it's going to help us make a step like maybe closer to here. So it's just going to make it a little bit better. It's going to make it a little bit better for us in scaling factor to penalize the very, very large weights. Okay, and for the cost, it's going to be very, very similar, except for we do need to incorporate our lambda, our extra thingy. We're going to do mostly the same stuff. It's just going to be, because we need to still have our cost entropy loss, but with the regularization that we need to also get the squares of the weights in order to kind of make up for the super small scaling factor. Right, and then backwards propagation is going to be where in a way the magic actually happens. We're going to take the same back propagation that we have here. This is the exact same thing that we had before, but we also need to take lambda times W3, which is going to be our weight, over n, which is going to be the number of values we have. So just to make the mean of it. I'm going to do that here. We're going to do that for our second set. I'm going to do that for our third set. Return all the gradients. Any questions on that?
So is there a 21 someplace, a 21 of 301 embedded in that code there someplace for? Referring back to the.
Yeah, well, it's still back to this over here. The 23
yeah,
and 1.
or 23 and 1, yeah.
Yeah, it's still back to here.
Okay, that's where it's.
Because we're just going to reuse everything.
Okay, got it.
That's the reason that we have all the heat prop and lambda stuff.
Excuse me, conceptually, right? Why this helps? I mean, if we got overfitting, right? Essentially, our fit was, I guess, too perfect. sense, right? Which we achieve with that learning rate, right? Now, if we make the learning rate even smaller with, what is it called, regularization, right? We're making essentially learning rate even smaller, right?
Yeah, but because the problem that we don't just make learning rate smaller is because we want to not only punish because with regularization, we're essentially only trying to punish the very, very large weights. But with when we just we make our learning rate smaller, it'll do the exact same thing, but for the smaller weights as well.
Okay.
Sorry, did you say that? Regular?
The LT regularization, that will, it mostly only punishes large weights. Because we multiply the weights with the lambda, and that's pretty much, yeah. So we multiply the weights with the lambda, and that will scale down, it'll mostly scale down the really, really large weights, because we want our lambda to be kind of like, I don't even remember what a third lambda is, but we'll see in a second. But the idea is that we want to only penalize the very, very large weights, and we don't want to penalize the very, very small weights.
Hey, did you set, what did you set the value for the L2? Did you get to that cell yet?
I actually forgot, so I was going to look at that. I'm going to try to look at that in a second.
Because that makes a huge difference.
It does. Oh, in this case, I'm just setting lambda to 0.7.
Yeah, exactly.
So
Don't start at 0.1 or 0.01.
yeah.
Yeah.
Well,
especially
I mean,
with a
point
surface
one,
like that.
yeah.
Yeah,
So
terrible.
this will make the. So it all has to do with back to the loss function, the backpropagation here, because when we backpropagate through, let's say our weight is 7. Like let's say our weight is 7. We take our derivative. I'm sorry. When we take the derivative, and let's say that's 7. Then when we multiply that by 0.7, it's going to be 4.9. Then we just keep going in that sense, where it's going to get smaller and smaller and smaller. But if we have a weight of 0.1, it's only going to be reduced to 0.7. Or, I mean, if we have a weight of 1, it's only going to be reduced to 0.7, which is going to make it much smaller than the larger weight. And that's the reason that we use LT regularization as opposed to making a smaller learning rate. Because another thing about LT regularization, because you can think of the LT regularization or the lambda as just taking a percentage of the weight, and larger weights are going to have larger, like, part of them taken out, and then the smaller weights are going to have a smaller percentage.
Wait a minute. So maybe I'm talking something different. So the weight is actually 0.7. Maybe it's not the L2.
Lambda, the LT regularization.
Okay. When I set it in TensorFlow for L2, I usually set it to, well, I was setting it way too big.
I mean, it's all like kind of experimentation, because it's just a hyperparameter that you
But
can.
in the literature, anyway, so the difference between having the validation error going north and the test error going south at 0.1 or 0.01 versus e times e to the negative 1 times 10 to the 6, so 0.00000, 5 zeros and a 1. All of a sudden, the model came back, and I found a pattern. But thank God I found that, because otherwise it would have just
I
went
mean,
crazy.
it's all a matter of like overfitting, as you said, like the training validation, the training.
This is the LSTM.
Yeah, there could be also exploding gradients as well.
And maybe it's specific to the architecture too, I'm not sure. Like,
Architecture's
if that's
usually-
not a general
like,
thing.
Frameworks usually pretty fine. So, completely besides the point of anything here with frameworks and everything. We're going to get back to this. So, if we take our shiny new model with our new lambda, we make our predictions again. loss function. Okay, and our graph is going to look more like this. Where we have this, the peninsula that was over here before, it's no longer there, and it's just doing a much better job. Sure that these are misclassified, but that's just noisy data. That's not too much that we can deal with.
I think
You
it's
should have a cutoff in the weights rather than lambda.
So what's that?
Why don't you just have a cutoff?
Oh, like weight cutoff? I find that using that doesn't help me quite as much as doing something like randomization. It definitely can help, but it would also require you to carefully and meticulously look at the actual weights and see where everything's going wrong. And in a model where you have thousands and thousands of weights, it's going to get really annoying really quickly. But you absolutely can like look at your weights and say like if they're above this value, just accept this value. Okay. Yes.
Yeah, I'm sorry, I didn't mean to interrupt, but just a little, maybe you could help clarify. So you got to choose how many neurons per layer, or how many layers and how
Yes.
many neurons, right? So you're doing that decision, and then your choice to add in, I might be saying it incorrectly, but to add in lambda into that. Like, wouldn't you want to optimize first on your network,
Well,
just to keep it simple
That's
without
also,
lambda?
that's
and
also
then
the reason
add
that we
lambda?
ran the model on nothing before. Because we ran the model just with this and we did this. So then in my mind I'm saying, okay, this is really bad. We're overfitting like crazy. So the simplest solution first is going to be the lambda, which is going to help like a little bit.
Just as a factoid, I ran it with the L2 at the lambda at point, 5 zeros and a 1, and your cost function, the first one was 0.1759, and the second, when I did it with that smaller L2, it landed at 0.1149.
The very, very first loss function? Or
I forget what cell I'm in, 20, where is it here? It says parameters equal reg model train X, train Y, lambda equal 0.7. Prediction. So that's cell 21.
Okay.
And so the cost after iteration, the 30,000 was 1759, 65, whatever. Learning rate is equal to 0.3. And just changing that one parameter dropped it to, well, first of all, it dropped like a rock. So this sort of surfed 17 all the way down to the bottom. This one went from 0.65 to 0.13 to 0.12, and then 0.12 for a while, whatever. So it did a much better job. Accuracy is 0.95. That's the accuracy.
Yeah, just it's a
so in grand scheme of things, yeah, it's a half of whatever, a tenth of a percentage point. But
Yeah.
But if you were to graph the predicted and the actual data, you would see that it actually, the trend looks more, the model looks more like the data when you're doing it anyway. I just learned that this week the hard way. I'm just sharing.
Next we're going to talk about dropout, which is another important concept. So with dropout, we have so here's our network, as we know and love. With dropout, all we're going to do is essentially just turn off layers in the middle. So during training time, not during testing time. The motivation behind this is that when something goes through, like when our data passes through, our model could just be using this this neuron and this neuron, and these have like very, very small weights, which means they have very, very little effect on how the actual output is. But these have very, very large weights, which means it's probably going to generalized for only very, very specific cases. So we might as well just have something that looks closer to this. The idea behind dropout is that during test time, we're going to randomly turn off some of these, and then that will help the model have like less over-reliance on each weight. So we can turn this off, and then these ones are forced to learn, the ones that were for not learning. That's essentially the motivation behind there. And then during test time, we obviously want to use the entire model, otherwise it's we're handicapping our model. So we're essentially, during training time, we're handicapping our model on purpose, and during testing time, we just want the whole thing.
Now, when you're talking about it forcing the nodes to learn, is that data, the results from that being retained and reused by the model, or is
Well,
that something we observe and then make an adjustment?
Can you repeat the question? I'm sorry.
When you were talking about dropping out certain of the variables or the nodes, I'll call them, so that the others can learn better. Now, having run that through, is that learning retained someplace?
Yeah, we're going to still retain the weights. We're going to still retain the biases,
Mhm.
but it's just for that particular case, we're just not using those.
So the learning is expressed in adjustments to the weights? Is that-
Yes.
So is the concept behind that, is that because you might be getting some neurons, like finding some local minima or something? And then you drop them out, like it's forcing.
In a way,
something-
in a way, yes, but it's mostly to counteract overfitting.
Right.
So if we go back up here to our super overfitted function, we could say that, okay, right here, maybe it's just 10 of the 20 neurons that are like really, really responsive to this, really giving bad information to the next set of neurons because they have ginormous weights and they have such a big pool. So we're just going to lower that a little bit, which is going to lead to this, which is going to lead to a much better. Yeah. And then in turn, if something does develop very, very large weights, the model will, since everything else, so if this weight is absolutely ginormous, and the rest of these weights are much smaller, when these start to get a little bit bigger, they're going to have essentially more pull, which is going to make this one start to get smaller as well. So, with dropout, so we can see, yeah, when we're doing our actual dropout, we're just going to set our D, our dropout. It's going to be a probability of 0 or 1, or of not 0 or 1, probability. We're just going to make a probability between 0 and 1, a percentage of how many weights we want to drop out. And it's going to be completely random, as we can see here. So we just want to take the shape of our activation, and we're essentially just going to not send data on through to the rest of the network. And we're going to do the exact same thing here and multiply it with the activation to just make that go to 0 this time, and then set, yeah. So backpropagation with it as well, we need to, in a way, set a mask, because when we are going through this network, and this one was turned off the whole time, we don't want it to try to update this one. So you have to set a mask to say, hey, just ignore this thing, which is going to be what we're doing right here. We're going to take the D2, which is going to be the same D that we had from before, the neurons that we want to shut down, and just shut the exact same ones down. And then we need to scale it back in order to make up for the ones that were shut down. And now we run it with a keep probability of 0.5. This works. There's like a divide by 0 or something somewhere that I must have missed, which is why it's stand. So sorry about that. But we still get the results. So we can see that here, it's getting a little bit better. The accuracy is 97%. That's better than I expected. And we can see how dropout will affect it, because we have, with a much simpler model, we'll get much simpler equations essentially, right? So if we have a model of 20, and our keep probability was 50 or of 0.5, it just means that we're going to only use 50% we're only going to use 50% of the neurons. So we can see that this is a little bit simpler, as we don't have the robustness of all the curves and everything, but this is still a very, very good model. And you may not even need all of the robustness. So,
October 15th.
yeah. This is. Oh, okay, so. What was the next? Okay, so now we're going to move into the area of regularization, which we're going to talk about root mean squared, not regularization, optimization. We're going to learn about root mean squared and the atom optimizer. So what these will do is, how we learned before is we had our graph, and then we would take just take a small step. But we may want to increase the step size or decrease the step size adaptively. So that's essentially what we're going to be going for here. Okay, this is less important. Okay, so first we're going to have to worry about doing mini batches. Where the mini batches are going to be subsets of our data, going to be the small subsets of our data. So as opposed to taking our data as a whole and just passing the entire 300 data points every single time, what mini batches will do is that it's going to just do, let's say, 5 at a time, and then we're going to backpropagate with that, and take another 5 and backpropagate with that. And yet, so part of the reason that we want to do this is because we'll get a much more, in a way, more accurate, we're going to get we may get a smaller step, but we're also going to get a more accurate step, in the sense where we're going to be sure that we're stepping the right way each time, and we're also going to get results a little bit faster. So, in a more intuitive way. So if we have, this is always the classic example. So let's pretend we're playing track practice. We want to get to this local minimum. This is 3-dimensional, but 2-dimensional. Yeah, 2-dimensional I'm talking about. So with our gradient descent that we've learned so far, our backpropagation that we've learned so far, we may move here, we may move here, we may move here, we may move here, keep going, like that. What mini batches will do is that instead of doing this whole line, which is 300 data points, we may go here, and then we're going to go here, then we're going to go here, then we're going to go here, and then we're going to go here. And it's going to be a much smoother line that's going to help us get to this faster. On top of this, it also helps for lower powered machines, because a lower powered machine, a lower powered machine may not be able to hold a super complex, ginormous data set of 4K images. But if we just do by 5, it only has to do 5 4K images as immediate memory at the same time. So that's the idea behind the mini batches. And so we're going to first learn about velocity, which is going to be what the idea behind momentum is. So just from the idea of being able to roll a snowball down a hill, or roll a ball down a hill, or literally roll anything down a hill, we're going to, if we have a function that we're trying to graph like this, usually what we would have done is we would have gotten here, then we would have gotten here, then we would have gotten here, then we would have gotten here, and it's very small iterative process. With momentum, we can say, it's essentially saying, we get from here to here, and I'll say, okay, did I guess right? Okay, let me move a little bit farther in the same direction this time. Okay, let me move a little farther that direction this time, and then it'll just keep going like that. That's essentially the idea behind momentum. And the idea behind when we update parameters with momentum is here, where we're going to take the actual the beta, which is going to be our momentum, is how much, essentially another multiplier based on how much we want to. How to describe this? It's an additional multiplier based on how much we want to tell our model how well it's doing, in a sense. Because if we have a very small beta, it's just going to, as you can see here, this will just be multiplied by essentially 1, which is going to do the exact same thing as doing no beta. But a very high beta it'll give it'll make it, yeah, it'll just keep going more and more and more, and even though the beta will start out very small, it's going, I mean, not the beta, but the gradients, they'll start out very small. They'll just keep getting bigger and bigger and bigger over time because of our back propagation. We just keep going over and over and over. Okay, sorry, I absolutely skipped over this. So another way of doing it is that we will take our what we can do is that instead of just doing the, is it anything? I'm actually silly. I'm sorry. Okay. Okay. I know what I'm doing now. I'm sorry. We have the velocity, which is different, which is another different thing, which is just where we're going to take our. It's another parameter, as opposed to the momentum is going to be velocity, and that's going to do a very similar thing to momentum, where if we so with momentum, we'll be able to start off very small, and then we'll just keep going and going and going and going, right? However, with velocity, it's going to be in a way the opposite. But we're going to start off a bit larger in a prediction that we're confident in, and then we're just going to keep going and going. But at some point, it's going to say, at some point, we're going to get to the idea that we're getting close to the global minimum. So we want to just slow our velocity down to, it's the idea of being able to take step sizes. So, with RMS prop, which is a optimizer, it kind of does both. So it will it'll behave very similarly to momentum, but instead of continuing in the same direction, it'll find the root mean squared of the gradients. which is essentially a combination of velocity and momentum. And then we have the RMS is without velocity, but it just uses an altered form of momentum. So with that we have the adaptive moment estimation optimizer, which is otherwise known as ATOM, and that will, in a way, so what we had here was that we start off fast, go slow, start off slow, go fast, and this way we're going to, with the adaptive moment estimation, or ATOM, we're going to be able to learn. We're going to be able to learn how fast we should go and how slow we should go at each time. So it uses a moving average and uses the velocity of the momentum. And the moving average, what that'll do is it'll essentially say after, usually it's about 10. After 10 iterations, just kind of forget about those. So we only want to care about the last 10 or so. And then velocity is just this. And momentum, and it draws momentum through velocity and S, where it uses the idea of momentum where it starts slow and may go high, but then it just forgets about anything that was too far away because we don't want to care too much about those gradients. So here is the actual optimization algorithm, written very, very beautifully, of course.
So does the A in ATOM stand for adaptive, and then the DAM, or was it some guy named Atom?
No, it's APA, which is adaptive, and then the M is moment estimation. So here's the actual algorithm behind ATOM, courtesy of, not courtesy because I don't think they gave me permission. Yeah, they definitely gave me permission, but it's probably fine. Of Coursera, Andrew Ng's Deep Learning AI course, which is great. What we can see here, the entire update over a mini batch will give us the velocity and the moving average. We're going to take our, it's in simplest terms possible. It's a simpler form. It's like a more complex form of the back propagation algorithm that we were looking at before, where we take the chain rule and just keep going backwards and backwards and backwards, just adding more terms that will help update the weights over time. So there's that. It's going to have two hyperparameters, beta 1 and beta 2. Beta 1 is going to be for the velocity, and beta 2 is going to be for the other one. Shoot, what's it called? The moving average, sorry. Beta 2 is going to be for the moving average, and that's going to, we're just going to multiply each one by usually about 0.999, I think, and beta 1 is usually just 0.9. These are hyperparameters, but they tend to remain untouched, but you certainly can play around with them and just kind of see what you can do with them. And so here is the actual updating of the parameters with ATOM. We're going to take the velocity of the DW, multiply it with the beta 1, which is going to be 0.9. Mixed with multiplied by the velocity of dW, time minus the 0.1. Well, yeah, plus 0.1 times the rate. Okay, that was a jumbled mess of speech, so I'm just going to go back over that in hopefully cleaner terms. So we're going to set the velocity of dW to beta 1. Beta 1 times the last velocity, and that's how we're going to update it, multiplied, plus 1 minus the last weights the 1 minus the last weta, 0.1 times the weights. And then we're going to do bias correction, because when we do the actual updating, the bias still will come into play. So this whole bias correction idea is in order to try to just let that not happen. The moving average is going to be a very similar formula. There's going to be the beta 2, 0.9999 times the last moving average minus 0.0001 times the last weights squared. And we're squaring it because this is going to be a very, very, very small number, and we want to A, make sure we're not getting any negatives, and B, try to just scale up a little bit more. Okay. So that's, yeah, so, and we're going to do the exact same thing with the correction, where the SCW is going to be 1 minus beta squared t, which is, t is the time step. So we want to reduce, so ideally what we're doing is we're going to do 0.999 times 0.999 times 0.999. So that's going to that's going to just keep making the betas smaller. That's how we're going to forget about the last weights. By essentially just constantly, like,
Giving them a lower weight.
yeah, essentially just giving them a little bit. And this will just be with our normal gradient descent as we've seen before. It doesn't bad. I mean, not too bad, I guess. Now we're going to try it with our memento. Well, I must have set this to a much lower epoch, so it's obviously going to do worse because that is quite as long to learn what it's doing. So yeah. And that is very, very messy, but you can still see that there's an obvious curve on how well we're doing over time. And this will do much better. Something that I thought was interesting with this is that it sometimes overfits in a way where it doesn't worry about stuff that's outside of what it overfits. This makes absolutely no sense. But the idea is that with L2 regularization, for example, it was able to get the entire thing, like everything down here, with our momentum. It just cuts off. So it overfits to a very decent model in a way, which makes weird sense, but. And then we're going to try with Atom, and I didn't run that cell. And we're going to let that go as well for, I guess, 10,000 epochs. Another thing worth noting is that we only have the layer dimensions. Yes, I've been changing them throughout the time, so I've only been using shape 5 to 1. And with that, this is much more robust than the momentum model, even though they do have the same accuracy. But overall, the predictions that this one's making and the actual graph of what this looks like seems like it's making a much better like much better predictions as a whole. So if you have any questions about any of those. Are you sure?
How do we know what optimizer to choose?
So, Atom tends to be pretty standard. There's Atom and there's also 100 million variations of Atom. What I've always used is either I've just used gradient descent as a sanity check, but then anything else that I actually want to make usable, I usually just use Atom.
And is there any parameter that we look when we are comparing two optimizers?
Um,
How to make out which is
It's
better?
it's less about a parameter per se, and more of just at this point it's an industry standard. Because with Atom, it's able to essentially in a way learn. It's able to learn its own learning rate. It's able to learn how much it wants to step at each time step, even though we do give it something that it starts with. But by using Atom, it's going to do better than I personally think it's like better than this right here with just like RMS prop. It certainly is better than this with the exact same everything essentially. Yeah, because this even has the exact same number of training. This has the exact same structure, the exact same number of epochs as the gradient descent. It does just this much better.
What's the accuracy on the just kind of two straight lines?
88%. Which like isn't
Very elegant.
yes. I mean it's really not that bad in a sense.
Yeah.
It still has like it just has to listen to this or
Yeah.
take up such a decent percentage. But usually it is just Atom or its variants that you would want to use. You're more than welcome to experiment with different things. I actually think I saw. Let's see if I can find it very quickly. This also is not these are not the only learning rates that exist. But we can see just these learning rates. This will be our graph. These will be our different learning rates, where you can see that Atom will go over here, and you can see how Atom works, how it's very, very confident in itself. And then when it starts to go somewhere else, it will very, very quickly correct itself. Where GD, gradient descent, is going to get stuck in a local minimum. RMS prop is the other one we talked about, and that is, as we said before, it starts off a little bit slower, and then it just works its way, but this also will end up getting stuck in a local minimum.
What's the gray one that is so angular?
Oh, the FTRL. This one?
Yeah.
Honestly, I'm not very familiar with FTRL. Let's go to the documentation. Yeah, it's something that I've actually never used. So it's hard to say that I am not sure. But we can see how essentially each one reacts. And what's extremely interesting is that the FTRL goes very, very quickly and things that's very, very confident in. We can also see that it seems like it's also getting stuck in a local minimum as opposed to the
Oh, in a different
in
scenario.
a different example. So it possibly it's just very, 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 it gets very, very confident very, very quickly.
Yeah, it's too cocky.
Which might, it's too cocky. It just thinks it knows where it's going. Sometimes it guesses right in the first example, and sometimes it guesses very wrong. My guess is that it's a learning rate that's very, very good for very, very quick experimentation. But as we can see here, that Atom and even just using momentum work very, very well here. And Yeah, wow, this is a very extensive GitHub page. This is the one I was thinking of. Like, just this is, I don't know, it was these two that I was thinking of. How we can see that some start off very, very slow. Some will find it here. Something that's interesting to me is that the red dot right here, which is standard gradient descent, stochastic gradient descent, it's very, very bad right there. But usually what's very nice about stochastic gradient descent is that it'll always essentially, except in this example, if you give it enough time, it'll always move somewhere. And it'll always get to a place that's close to where you want to get, which is why I always try to do experiments with gradient descent first, and then I usually just move to atom.
Is the link to this visualization within today's lesson?
I can put it in today's lesson. I literally just Googled optimization
Oh,
visualization.
wow.
But no, it is. So that should be there too. I also had an additional reading at the bottom as well, which is by this person who is a Korean person who is very good at just implementing everything by hand. And yeah, he's also very good, and he'll just tell you more about different algorithms as well. So yeah, so any other questions or anything that's tickling your curiosity? If not, we have 8 minutes, so you're all just going to be held hostage.
I do have, again, maybe a conceptual question. And then I'm trying to, like, something you said where you start with one and then you end up switching to atom, right? You start with stochastic and then, so if you have your answer or you have your model, like, what's the point of going to atom at that point? Like, you have.
It's more of the idea of, if we go back to here, that sometimes stochastic gradient descent won't always work, but it's usually relatively reliable. And in here's what I mean, where it's very, very low cost. It doesn't have to do quite as many calculations as, say, atom does. So it maybe will calculate a little bit quicker, which is what I've found, which is why I usually use it. But it'll still get to about to where it's going, but it needs that extra push, which is why atom will be much better.
But so, like, what's the trade-off? Like, so I'm trying to understand, why
okay,
would
okay.
you...
So
are you trying to save computational cycles or something?
it's less about the computational cycles and more about my time, because if we saw here, it takes a couple seconds to run one of these models, but with a real deep learning model, it takes hours. So I just want to make sure that I'm going in the right direction before, like, proceeding too much further forward. So
Stochastic first and then...
it's usually what I do. You're more than, like, I think most people just use atom first, but I guess I don't care about my time code as much as most people. So I think most people just start with atom and only use atom just because it tends to be better than, it will be better than the stochastic gradient descent at least. But it tends to be better than all of its other competitors.
Just very simply, so a stochastic gradient descent would be like online learning, one sample at a time, update the weights.
Yes.
The opposite would be read all the data in and do the weights like we do normally in statistics or whatever. And then there's what I understand to be called mini batch. Is that what Adam is doing, optimizing
Well, the
the
mini
batch
batch
size?
is just like
Probably more, but
just batches. It's just like batches upon batches. So you're taking a batch out of the, that's closer to like the online learning example that you talked about. However, online learning is something a little bit different, but it's completely besides the point. Where a mini batch will take a batch, it'll take a batch of 32, and then it'll take a mini batch of say 8, so it'll do 8 updates within that batch. So it just making it much smaller and trying to get.
So it's multiple data points, and it's probably normalizing it, or do you have to add batch normalization to that,
You have to add batch normalization.
to Adam? Okay.
Naturalization is
You don't have
something
to
that we did
look
not
at
cover,
it.
and we're not going to cover. So,
Yeah.
sorry about that. It's actually just got patented, which is,
There's too many dials to dial. It's like, where do I start? Like, well,
yeah, but
anywhere. It's like, well, you mean
dropout-
nowhere.
The dropout thing that we talked about earlier got patented by Google in 2015, and something else, bad formalization, got patented like just a couple days ago actually. There's a lot of backlash about that because somebody said it's like patenting like the Fourier transform, like just something that you need in order to do your stuff, but Google's crazy. Don't put that on YouTube.
Well, it's kind of like the same reason you scale the data. Even if you scale the data, if you're just taking chunks at a time, and the scale is defined by the first chunk that happens to pop into the algorithm, it kind of sets the tone for like the next move. And so if you don't rescale for the different chunks of the data, then it just makes it that much harder for this crazy, Medusa type algorithm to figure out where it's going, or where should it land. Anyway.
So does anybody else have any other questions? Yes.
So would you have any suggestions of tools online that we can get started for, like automated machine learning?
For AutoML?
Yeah.
So,
Azure has one set of some of the stuff.
that does it. That's actually great. But the people who like wrote the initial like AutoML paper are the people behind Salesforce. Like MetaMind is what their research group's called.
There's a data robot also something.
What's that?
Data robot?
Wait, I'm sorry. What?
There's a tool like data robot.
Data robot, you
Yeah.
mean?
Well,
Oh,
like
I don't know.
I'm not
So.
sure, but I mean like Salesforce is like just like the CRM thing, but
Yeah.
the research group is the one that came up with like AutoML and like really helped their platform, and then they ended up open sourcing it, which was unexpected. But they wrote the initial AutoML paper. Honestly, I'm not super sure what about too much learning resources regarding AutoML, so I'm sorry about that. But I at least know a couple papers, which is kind of just like how I pretty much know the overall concept. I've never gotten too far into it.
Sorry, so getting back to this here, I mean, what is this? This is Python ML or
What's that?
what is this thing that you're doing here? Is this thing?
It's Google. It's Google Colab.
Hold that.
Yeah, so it's really super nice because all the packages that you need are usually already installed. It just works all through your browser, so you don't have to worry about your machine. It uses Python, so it's not restricted to doing ML things. You can usually I just open a Google Colab page whenever I just want to do like a really quick experiment with anything. And sometimes you can just say, hey, check. I think I have a couple of notebooks that are like 2 lines long.
So, I mean, so how does this work? Each one of these are little paragraphs
Yeah,
or something?
they're each called cells. It's all based off of the IPython notebooks.
Okay.
So each of these are little cells, and they run independently. And the super nice thing about these is that you can run this by doing Control Shift Enter or Shift Return. You do need to sign in Google first,
Okay.
but you can run this, and then you can run this, and everything from this one up here will still be retained. So it's very good for rapid experimentation. So if you run something here and it just does not work, you can keep moving on, or you can go back, change a few things, and instead of
Oh,
like,
but whatever's in here is made available to the second one?
yes, which is also like this is also available to the third one, the fourth one, and everything is just stays constant. So yeah, Google Colab is super nice.
So, okay, so when I go home, and I want to do this at home, right?
Yes.
I'm gonna log into my Google.
Yes.
I'm gonna go to the Colab page.
Yes. Or you can go to
Or,
Meetup first.
or Meetup.
Or you're gonna have to go to Meetup to access the Colab page.
Right, which you created for us, right? Or
Yeah.
was, yeah, right?
Well, which one? I didn't
The
create
one that
video.
we've been looking at.
Oh, yeah, I made that one
Yeah,
a couple days ago.
okay. And then from there, we can run stuff.
You
Now,
can just
if-
run
or experiment with it and try to figure out what it's all about, right?
Yes.
And then when you're ready to take the plunge and do something yourself, you go to Google Colab.
You can
Oh,
go,
it's
you can go.
way easy.
It's
Come over to my house, I'll type it up for you, it's very easy.
All right, yeah, okay, yeah.
You can go to Google.
It's so
Colab.
easy, I dropped everything, I don't have a laptop, and I just log in through like.
Oh,
Chromebook,
serious?
Yeah.
Wow,
Oh, it's just phenomenal.
great, all right.
I've told so many people, I'll stop doing it.
The only big
Yeah,
drawback
probably, right?
of Google Colab though is that it's hard to do entire projects because sometimes you'll need multiple Python files within everything,
Right,
which
yeah.
which you would have to open your text editor. You can put all the files into your Google Colab, but it's just kind of
Yeah.
awkward to use.
You can't store data
So-
files there, they don't want you doing that, and, you know,
Right.
but you can run it off your drive.
Can
or
you
whatever.
combine it with, say, for example, whatever their cloud solution is, kind of like AWS?
Well, they want
but
you
their
to do
version?
that.
Yeah,
They
right.
absolutely
Then you
want
just
to
gotta
do
pay
that.
every month.
So if you want to deploy something,
Yeah.
you're not going to do it on Colab. You're going to have to figure out. Well, maybe have you tried when you did the reunion project? Did you run that? Run anything off of Colab, or we had moved
No,
everything
because
to
the problem with
AWS?
Colab is that it times out. So like after
Mm.
an hour of being left idle, it'll just reset everything, and then all of the models that you trained, if you didn't save them, are gone. All of everything else is gone.
Their memory's been wiped.
Essentially, yeah. So
no.
unless you go
Yeah,
go ahead
unless
and
you
save
store
it.
it.
So that's like the reason why I don't know. Like I have like a computer that like I use for this stuff because the most important part is like the GPU. Because gamers like graphics. A couple of years ago, people saw like, wow, these GPUs are really good for complex matrix multiplication, which is what we're all doing, which is what we're doing here. And that's why GPUs are very good for deep learning. Which Google Colab does allow their GPUs and TPUs available through Colab.
Now, does calling these routines from Python automatically route GPU appropriate calculations to the
Not
GPU, or do
quite,
you
so-
have to somehow or another like
I can show
tell
you
it to?
really
You
quickly.
open the notebook up and you
Yeah.
tell it when it's in your notebook if it's CPU, GPU, TPU. I have not.
So you gotta kind of know what's good for what.
The fastest is always the best, but I don't, I try not
Yeah.
to overstay my welcome, so
Uh-huh.
I'm happy if my
Yeah.
stuff runs in a reasonable amount of time. And
Yeah, also, guys, it's like 8:03 at this point, so if you want to leave, you are absolutely more than welcome to and encouraged to if, you know.
You know, like,
Sorry.
Not that it's like, but it's like, you know, you guys
it's free for a
probably also
reason,
have lives.
you know.
Yeah, uh-huh.
They want researchers
They
to
want
go up
people to-
there
yeah.
to actually do research in deep
And
learning.
do stuff, yeah.
Right, and so they'll let you do pretty much what I did non-deep learning stuff like mixture models and things like that. So it's not going to stop you from
Right.
doing it. Just understanding directory structures and stuff is a little funky, but
Right,
once you
yeah.
get it, it's very easy.